Okay, welcome back. If you remember, over the last few lectures, we were looking at some simple real time task schedulers. We had looked at very simple schedulers like table driven schedulers, but then we saw that it had its disadvantage requiring to set a timer again and again after each task's execution. We had remarked that time that the cyclic scheduler is extremely popular because it does not require setting a periodic timer again and again. It just needs to set it once during the initialization. It requires two design tasks to be done. One is to set the major cycle for a set of periodic tasks, and then also to set the minor cycle, which is also called as a frame. Major cycle is rather simple to compute. If you remember, it is the LCM of the task periods, but then setting the frame size is not that straightforward. It is non-trivial. We need to consider several design alternatives and may have to iterate between our frame sizes. Maybe we have to split the tasks and so on. So, setting the frame size is an important design task while using a cyclic scheduler. Let us see how the frame size is to be set. The first consideration is that each frame size must be larger than the execution time of every task. If you remember why this is so, it is because every frame size must hold the task, or in other words, if a task is taken up for execution in a frame, it must complete within the frame. It should not spill over to the subsequent frames, and that is the reason a frame size should be larger than the largest task execution time. So, based on this consideration, we get a lower bound for the frame. The frame, if it becomes lower than the largest task size, then that is not a good schedule. It will have problems, as we will see. The second consideration is minimization of the schedule table that we have to store. From this consideration, we require that the frame size that is chosen should squarely divide the major cycle, or it must be a factor of the major cycle. Based on this consideration, we can select only few discrete frame sizes. If the frame size does not squarely divide the major cycle, then we have to store the schedule for several major cycles. If the frame squarely divides the major cycle, then after the major cycle the same task sequence will repeat. So, we need to store only the task schedule for one major cycle. The third consideration is every task must meet its deadline, and for this to happen, there must be one full frame between the arrival of a task and its deadline. To see why it is so, we need to consider that if a task arrives just after a frame has started, then the task cannot be taken up in that frame, and if its deadline also is within the same frame, then the task execution cannot be started before its deadline. So, we must have at least one clear frame between a task's starting and its deadline. A corollary of this third condition is that the frame size has to be greater than every task period. So, this sets an upper bound for the frame size. So, a frame size must be less than every task period. So, let us see, we will get more explanation on this as we proceed. So, the first condition is that the frame size must be chosen such that every task must be able to execute in the frame size, because if that does not happen, then we have to run the task across multiple frames. So, in that case other tasks may run in between and they may use the partial results obtained by executing a task halfway or maybe partially, and that may lead to inconsistency. So, normally we would need that frame size should be larger than the execution time of every task. The second condition, okay. So, the first condition we just saw that the selected frame size should be larger than execution time of each task. The second condition is minimization of the table size. So, this is the schedule table which we need to store. The schedule table, if you remember, is for every frame which task is to be run. So, as the frame interrupts come, the scheduler just takes up the task by consulting the table. So, first frame it took up the green task, the second frame the red task, third frame yellow task, and so on. And after the major cycle, the same sequence repeats. That is because the last frame boundary coincided with the major cycle, and by this time all the tasks have run. So, this is the LCM of all the task period, and therefore, every task period also has the ending of that has coincided here. But if the frame boundary does not coincide with the major cycle boundary, it spills over, then we have to store the schedule table for many major cycles. And from this consideration, we get the condition that the frame size should divide the major cycle, it should be a factor of the major cycle, and that gives us only few discrete choices to select the frame size. Now, let us look at the third condition, which says that the frame size should be chosen such that every task deadline must be met. So, let us see what is the implication of this condition. Let us say we have this frame boundary starting at this point. So, we have the frame boundary starting at this point. Now, let us assume that after a delta time, after some time, the task instance T I arrived at this point. Obviously, the task cannot be taken up during this frame, because if you remember the scheduler code, that it just executes the task and then the scheduler ends. The scheduler comes up just before every frame, starts execution of the task, consults the schedule table, finds out which task to run, it runs and then it stops. So, it can only run a start at the starting of a frame boundary. but here the task has arrived just after the frame boundary. Obviously, it cannot run on this frame, and then it can only be taken up in the next frame boundary. But then when the task is started to execute at the next frame boundary, the deadline is very near, it cannot meet its deadline. And this condition requires that we must have at least one full frame between the arrival of the task and the deadline, because if there is a full frame existing here, let us say we have a frame here, then if the task arrives here, then it can at least be taken up execution in the next frame, and we know that the frame size is larger than every task execution time, and therefore, it will complete within the frame and its deadline is after that. So, the third condition requires that we must have one clear frame existing between the arrival of a task and its deadline. So, let us look at the satisfaction of the task deadline. We just saw that the worst case for a task occurs when the task arrives just after the frame has started, because if the task arrives towards the end of a frame, then in the next frame it can be taken up. So, the worst case occurs if a frame has just started and the task arrives. Now, let us compute how much is this, what is the worst case scenario, because every task, if it arrives anywhere towards the end of a frame, that is not a worst case, because it can immediately be taken up in the next frame. So, the maximum time a task would have to wait if it arrives just after a frame boundary. So, we need to do a little bit of mathematical derivation, and we will not really go into derivation, it is there in the book. Here we will just look at the result. The result is GCD, the frame size and the period of the task. So, the greatest common divisor between the frame size and the task period, that gives the worst case situation of how much after the frame starts can a task arrive. So, if the GCD is 1, then at most after 1 time unit the task can occur. So, from this consideration, considering the worst case situation, then we have f minus GCD, f minus pi is the waiting time here, because it cannot be taken up for scheduling during this duration, and therefore, it must wait for f minus GCD f pi, and then we must have another clear frame. So, as long as 2 f minus GCD f comma pi is less than equal to di, then we have a clear frame available between the task's arrival and the deadline, even in the worst case situation. So, the third condition we can write in this expression, and we will see given a task set whether it satisfies this, and then if it satisfies, then we can take the frame size as feasible, otherwise we have to discard that frame size. So, written down the 3 conditions here. The first condition is that the task arrives just after the frame boundary, and the second condition is that the task arrives towards the end of a frame, and the third condition is that the task arrives at least one full frame between the arrival of the task and the deadline. the first condition is that the frame size f must be greater than the execution time of every task. So, the maximum execution time of the tasks, even that the f should be greater than even the maximum execution time of a task. The condition that there must be a clear frame between the arrival and the deadline gives us this condition. In the worst case, 2 f minus GCD p I comma f, the task period and f should be equal to the deadline of the task that must be satisfied for every task I. The third condition is that the frame size must squarely divide the major cycle. The major cycle we have written LCM p I, and this is the integer division f, and when multiplied by f, if we get back the LCM p I, then we can say that the frame size squarely divides the major cycle. Now, let us consider the design trade-offs. We find that there may be several frame sizes which may become feasible. We call that as plausible frames, but then just because they satisfied the three conditions and have got a plausible frame does not mean that we have found a schedule. We have to check other things. The first thing we need to check whether the number of frames that we require to schedule the task exists. Let us say the task 1 runs 3 times in the major cycle. So, the period of the task is 1/3 of the frames of the major cycle, and the second task runs 2 times during the major cycle. So, its period is half the major cycle. So, we need 5 frames for these 2 tasks. So, the frame size must be chosen such that there must be 5 frames within the major cycle. Let us look at that. As we look at the example, it will become clear. If we find that multiple frame sizes become possible, then we need to choose the largest of those frame sizes. Let us say the frame size 5 and 8, both of these are possible. They satisfy all the 3 conditions, and also they give rise to enough frames where all the task instances arising during the major cycle can be scheduled. Then we need to choose the larger of the frame size, that is 8. Why is that? Why do we need to choose the larger of the frame size? A little thinking will show that at every frame boundary, the scheduler needs to run. So, if we choose 5 as the frame size, then there will be many frame boundaries compared to when we choose 8 as the frame size. So, that means the scheduler runs more frequently if we choose a smaller frame size compared to a larger frame size, or in other words, the overhead of the task scheduler becomes more when we choose a smaller frame size, and therefore, we always choose the largest frame size that is possible. So, the scheduler overhead is lower when we choose a large frame size. Now, let us take a few examples. The first example, we have 2 tasks A, B, and the first element here is the computation time. So, A takes 1 unit of computation, its period and deadline are the same. So, the deadline occurs exactly at the period. So, it repeats after every 6 time units, and before it repeats, before the next instance comes, the first instance must have been over. That is the implication of the relative deadline. The second task B, execution time is 2, the period and deadline are both 8. Now, our task is to choose the major cycle and the minor cycle. Choosing the major cycle is rather straightforward. We just take LCM of 6 and 8, and we find that the least common multiple of 6 and 8 is 24. 24 holds an integral number of A, task A and task B. So, we can see that there are 4 instances of task A, 3 instances of task B within one major cycle. So, within one major cycle we will have 7 instances altogether, considering both A and B. Now, let us try to choose the frame size. If you remember that the frame size must squarely divide the major cycle, that we get from the schedule table consideration, minimizing the size of the schedule table, and therefore, we can get 24, 12, 6, 4, 3, 2. These are the frame sizes that we can consider for the other conditions. Why not 1? We have not written 1 here, because the size of the task B is 2 and every frame size must be greater than or equal to the largest task size, and therefore, 1 we have not considered. Consider 2, 3, 4, 6, 12, 24. Now, let us see, start with the smallest frame size and see if that becomes possible to satisfy the other conditions. So, let us check f equal to 2, and we will check if there is a full frame existing between the arrival of the task and its completion in the worst case. And we had expressed it in the formula 2 into f minus GCD f comma the task period. So, 2 into f is 2, and therefore, 2 into 2 minus the GCD of f is 2 and the period is 6. So, the GCD of 2 and 6 is 2, and therefore, we get 4 minus 2 is 2 and 2 is less than equal to 6. So, this is fine. Similarly, we can check for the second task. So, 2 into f minus GCD f comma the period of the second task. So, 2 into 2 and GCD of 2 and 8 is 2, which is equal to 4 minus 2 is 2, 2 is less than equal to 8. So, frame size 2 is okay, and also the number of frames that it can give us is 24 by 2 is 12. So, 12 frames. To 7 of those frames we can assign an instance of A or B as required, and 5 frames will remain unutilized. Now, let us look at frame size 3. So, again we apply the similar conditions here, 2 into f minus GCD f comma P A, we find that it is okay. Check for the second task also, we find okay. So, even frame size 3 is okay, and we have 24 by 3, which is 8 frames available in one major cycle, and we have 7 task instances in a major cycle, and therefore, even this is acceptable. Now, let us look at f equal to 4. In f equal to 4, again we use these two expressions, and we find that both of these again become acceptable. But then the number of frames becoming available is 6, 24 by 4 is 6 frames, and we cannot schedule 7 task instances in 6 frames. So, not enough frames are available, and therefore, f equal to 4 we cannot choose, and no point in looking further ahead 6, 8 etcetera, because the number of frames becomes still smaller, and therefore, 3 is the largest frame size for which we can have a possible schedule, and based on this our design choice will be the frame size equal to 3. Now, let us look at another example. We have 4 task sets A, B, C, D with execution time of 1, 3, 2, 8, and their periods are 10, 10, 20, 20. Now, how do we find the major cycle? The major cycle is the LCM of the task periods, and here there are only 2 periods 10 and 20. So, the LCM of 10 and 20 is 20. Now, the next thing is to choose the frame size. So, the frame size must be larger than the execution time of all tasks, greater than equal to all tasks, and also it has to satisfy the other conditions. So, we find that it must divide the major cycle, and based on that condition we get 1, 2, 4, 5, 10 and 20, but then it must be larger than 8, and therefore, we have only 10 and 20 is the possible frame size. So, in none of these cases, so the frame size can be either 10 or 20. So, if it is 20 we have just 1 frame, and if it is 10 we have just 2 frames. So, in none of the cases we can have a schedule worked out, because we have 2 instances of these, 2 instances of these, and 1 of these and 1 of these in one major cycle. So, that gives us 6 instances, and we need at least 6 frames, but then we are getting only either 1 or 2 frames. We cannot schedule this task set. If you can see, the major culprit here is this 8 here. As we proceed, we will see how to handle this situation. This task set is becoming unschedulable. How do we make it schedulable on a cyclic scheduler? We will stop here, and we will continue the next lecture from this point.